Assalamualaikum and good afternoon everyone. We will continue chapter 3 on assembly instruction set for A051. In this part, we will learn about data transfer and also arithmetic. The instruction set of A051 microcontroller consists of 111 different operations, which can be grouped into 5 types: arithmetic, logical, data transfer, Boolean variable, program branchings. And there are a total of 111. These 5 types of instructions are essential for a microcontroller to perform various operations. The operations are arithmetic and logical instructions to manipulate data, data transfer instruction to move data from one location to another within or between various memory space, Boolean variable instructions to perform logical and data transfer of single bits, program branching instruction to control the flow of program execution. Data transfer instruction. Data is stored at source address and moved or actually copied to a destination address. The ways by which these addresses are specified are determined by the addressing mode. There are 28 different instructions for data type, which can be further categorized into 3 main types: move, destination source; push, source; pop, destination; exchange, destination, source. 5 addressing modes are used to access the data: immediate, register, direct, indirect, and index. Data transfer instructions involve data transfer within the A051 memory, which is divided into 4 distinct physical parts: internal ROM, internal RAM, special function registers, external RAM, internal and external ROM. There are 5 types of instruction used for data transfer: move, move X, move C, code memory, push and pop, exchange. For internal RAM, the instruction that move or copy data within internal memory spaces execute in 1 or 2 machine cycles. The move instruction allows data to be transferred between any internal RAM location or special function registers without going through the accumulator. In A032 or A052, with the 256 byte of internal RAM, the upper 126 byte of internal RAM are accessed only by indirect addressing, and the special function registers are accessed only by direct addressing. Some examples using the move instruction are given below. For example, move A04H, immediate 04H. This means it copy data A4H into accumulator. Move R3 to DH, immediate data, copy immediate data to DH to R3. Move 30H, move at R0 30H, copy the content of internal RAM location 30H to the address pointed by R0. Data transfer instruction that move data between internal and external memory use indirect addressing mode. This is for external RAM. We use the instruction move X to transfer data between external RAM and the A051, which is the accumulator is used either as the source or destination operand. R0, R1, and DPTR can be used to hold the address of the data byte in the external RAM. R0 and R1, both are 8 bits, can only point to external address ranges from 00H to FFH. DPTR, which is 16 bits, can address the maximum RAM space of 000H to FFH. Some examples for move X instruction are given below. Move X at A at R1, this copy data from 8-bit address in R1 to accumulator. Move XA at DPTR, copy data from 16-bit address in DPTR to accumulator. For internal and external ROM, there are times when access to a pre-programmed set of data is needed, such as when using tables of predefined bytes. This data set must be permanent to be of repeated use and is thus stored in the program ROM using assembly directive. Access to this data is made possible by using index addressing, where either PC, program counter, or DPTR is used as the base register and the accumulator as the offset. Then we use the MOVC to copy data from the code memory to the accumulator. Lookup table. A lookup table can be used to convert one number into another number in one-to-one basis, such as trigonometric and exponential conversion. The example here is a lookup table for square number, where the output will be the square of the input. For example, 2 input, output 2 square become 4. The lookup table is stored in ROM, which is non-volatile, to enable conversion to be done quickly. The data in the lookup table can be accessed by using index addressing mode and MOVC. DPTR or PC, program counter, will hold the base address of the table, and the accumulator will hold the offsets which point to the different data in the table. For example, this code, assembly code, will compute the square of an integer number between 0 to 9. We start with move A30H. This means it copy data from T0H into the accumulator. So we assume there is a number, we want to find the square of it, and that number is inside 30H. So first copy it into A, and then call square subroutine. So we branch to subroutine. So the subroutine starts with increment A. The increment A is needed to bypass the return instruction so that A at A plus PC will point to correct offset in the lookup table. So there is some adjustment there. So the instruction move CA at A plus PC, it will copy data in ROM to the accumulator and return to the main program. The table, we use instruction define byte. Okay, so 0149, this is the square of a number. Let's look into the detail of the code. So here is the address of the memory, and this is the content of the memory. So the content of the memory is translated by the assembler from the assembly language. For example, move A30H, the code is E530H. So this instruction will copy whatever the value at address 30H into accumulator. For example, here is given 04. So 04 will be copied into accumulator. Call square. So these are the code to call the square subroutine 120030H. Okay. So when it calls square, it will jump to this address, which is 30H. Okay. And then increment A. Accumulator previously was 04H, it will become 05H. Next instruction, move C A at A plus PC. So PC is the address of the next instruction, which is 32. 32 plus 5 is 37H. So the data at address 37H, which is 16 or 10 in hex, will be copied into the accumulator. Okay. So we see the square of 4 is equal to 16, or in hex is 10H. So let's say if you have any other numbers, for example 5 plus 32 will be 30. For example, let's say we have in the accumulator we have 6. Okay, 6 square is 36. So 6 plus 32 plus 6, and then this one will increase. 6 it becomes 07 plus 32 39 039. So if we see 039 is 36. Push and pop operations move data between an area of internal RAM known as stack and a specified direct address. The stack pointer is used to point to the address in RAM where data from the source address will be pushed or where data to be popped to the destination address is found. The stack is operating in LIFO, last in first out order, as shown below. So push data on the stack, pop, take out data from the stack, last in first out. This is shown as internal RAM. This is the stack pointer to point where on top of the stack. Push and pop instruction behave as explained in the following table. Push, first we increment stack pointer and then copy data in address to the internal RAM address pointed by SP. Pop address, copy the data from an internal RAM address pointed by SP to address and decrement SP. Okay, so push, increment and copy, pop, copy and then decrement. So only direct addressing can be used with push and pop. If the content of the accumulator we push or pop, we must specify the correct accumulator address. Example here, push 30H. Push 30H, first let's say the SP is currently at 07, so SP will become 08, and then place data from 30H somewhere in the memory location 30H 95 and copy it into 08. Increment, then we increment push 31H, increment as first push 31H, you will increment SP to 09H, okay, and then place data from 31H, which is 68, copy it into 09. Next, pop 30H, pop, take out data first, place data 68 into 30H, and then decrement the SP to 08H. Pop 31H, place data which is 95 into 31H, and then decrement SP to 07H. For this slide, I leave it to you to find what is the output after this operation. This one we have push, 3 push and 3 pops. The stack grows up in memory as it is pushed. If we push excessively, it can make the stack exceed 7FH of the internal RAM and result in an error. The instruction sequence below illustrate some instruction for using push and pop. Okay, that's all for now. We'll continue in the next video. Thank you.